Okay, for ion selective electrode, there are different ways to make an electrode based on different theories. So this one is based on ion exchange. So for electrode, first of all, you need a conductor. So this is silver. Silver and the internal filling solution. In this case, it's calcium ion and chloride anion. So it depends on your analyte. So in this case, calcium 2 plus is your analyte. So you will dissolve calcium chloride inside. Okay, so this is internal solution. So now your internal reference solution will contain just the calcium chloride with the silver wire in it. So now this is your conducting internal solution. So the internal solution is going to be stick into ion exchanger. So this is a resin or polymer, which is an ion exchange polymer. And calcium will be associated with the resin. So we will learn more on the meaning of ion exchange. But here is polymer, and it is not water soluble. So calcium ion is going to be in there. So calcium ion in the ion exchanger, so they are ions, so they still have mobility. So now you have an internal calcium 2 plus lineup. So you have an internal potential to begin with. Okay, then you have a porous, thin layer, disk, porous membrane. So externally, this is your sample. Your sample analyzes calcium 2 plus, so you have a difference on the potential. So internal ion lineup, external sample analyte. So you have a delta E to measure the difference in the potential. Then you can measure, measure the calcium activity. So this is Nernst equation. Whatever you measure, then you get that. Okay, then for calibration, then you would use a known concentration of calcium so that you can set for the K and make a calibration line. Okay, then your unknown will give you a reading. Then from the calibration line, then you can get the concentration of your unknown. So any question with the drawing picture? So just keep in mind, here's the key thing. This is your resin, your polymer resin. Calcium ion will be loosely attached to the resin. So the calcium 2 plus is still mobile within, okay? Because you have a constant supply of calcium from here, so between the two, you're going to have calcium 2 plus immobile, so you will have a constant potential inside, okay? Any question with that? So interference for this guy, H plus may interfere with whenever the H plus concentration is greater than 10 to the minus 5. The H plus can interfere because of the plus ion. So in terms of your pH solution, then you don't want to use a pH lower than 6 solution. Okay, your sample solution cannot be less than 6. Otherwise, you will experience this interference. So generally a question, if I ask you how can you minimize or even avoid this interference if you are provided with a pH 5 calcium solution, how would you do it? If you are, I just hand over a solution and tell you this solution contains calcium 2+, and its pH equal to 5, but you will need to measure the calcium by using the electrode, this particular electrode. Then how will you make it to work in the lab?
Make it more acidic. Less acidic. Less acidic.
Common sense by now, you know, when you
Add some NaOH.
go to the real world. You're close. Who else volunteered?
KOH.
Huh?
It's some KOH.
Put it in layman language. Put it in layman.
A basic solution.
You can put an internal standard of your calcium.
We'll look it up in a book.
Make it more layman. Lay back and say, put buffer solution, right? You should know that by now, right?
Wouldn't you want to put an internal standard in here?
You just put a buffer 7, right? Buffer 7 in it, then it will work.
But wouldn't you want an internal standard?
No, nothing, no need. Because here, now the knowledge, you know, you just know that, you know, the H plus can interfere, right? So, so why not get rid of it by putting in buffer solution?
So you just calibrate it once and then, but you calibrate it before the fact?
Well, all your analyzed solution would be buffered to pH 7, right? So
we're not.
calibration line should be the same as your sample.
Is there anywhere
And Jeffrey was close, and with sodium hydroxide, not potassium hydroxide. You are close, but you know, buffer.
I meant HCl and.
Okay, then if you put KOH or NaOH, you could run into this problem, right? So if the pH is so high, then you get a precipitate. So what it amounts to, you must work in between this range, within this range. Okay, so pH 6 and pH 11. Within that range, and therefore use buffer solution. Otherwise, how do you know, right? Okay, so that's some practical understanding, you know, it's simple stuff. Okay. So another way to make this kind of electrode, ion selective electrode, is, you know, simply do a solid state. So-called solid state, this is solid. Internally, you still have a solution. So when you get a solid state electrode, don't assume the whole deal is solid. It doesn't mean that. Okay, so you will have a internal reference solution. So once you have that electrode, then now the external one is going to be dependent on whatever your substance of interest is. In this case, it's an anion, F minus, so you can prepare sodium fluoride, for example, or KF, potassium fluoride, 2.1 molar as your reference solution. Then this is solid state, so-called solid state is a solid crystal. Okay, it could be, what do you mean by single crystal? It's not just one piece, one grain of crystal, it doesn't mean that. So-called single crystal is single chemical. Okay, a pure chemical. Okay, single, in my example, is lanthanum fluoride is a single crystal. But it could be mixed crystals, okay, different chemicals to make the crystal, or it could be mixing with polymer material, you know, multiple crystals and mixed together, fused together, kind of thing. Okay, let's use the simplest example for understanding. So lanthanum fluoride, so you pack this crystal as a disc and stick in, hold it, you know, with O-ring or something, or you can use epoxy glue, simply glue it to that. Now, this is the crystal, solid crystal, and here the internal fluoride. Okay, your analyte is external, fluoride. So you have different ion line up internally as well as ion line up externally. You have fluoride as a medium to conduct the mobility, so it's ion mobility, so it's going to exchange, right? The fluoride, internal, external, so will give you the mobility. So now you have the internal activity being constant, and here external activity is different. So now you have the two, internal, external, so you can have a delta E. This is how you measure, okay, the fluoride concentration. So it is because you specify the fluoride as a crystal, so it's going to be selective for fluoride, and make sure your internal solution is common, the anion is common to the anion on the crystal to make it to work. The OH minus could interfere, okay, because this is minus and this is minus as well. Now the H plus likewise could interfere because the H plus can react with the F minus to form this. Okay. Then our knowledge of selectivity. So usually, whenever it's selective, then it's usually the 1,000 to 1 kind of selectivity. Okay. So fluoride is 1,000, but these other anions, the minus ones, okay, is 1. So when these concentrations are high enough, then they will interfere, give significant signals, okay, and therefore interfere. Okay, so any question with that?